Hello everyone. So a very good evening to everyone. I hope you all are doing well and putting your effort in the preparation of GATE exam, and it is just at hand. And I think in the first week of February we will all face the GATE exam. So what we are discussing about the fault analysis in power systems, and we have covered the symmetrical fault analysis concept, and we have also solved gate previous year problems based on symmetrical fault analysis and symmetrical component theory. We have also seen the sequence impedances of transmission line in the last session. Now today what we are going to do, we are going to see the unsymmetrical fault analysis. And before we come to the today's topic, let us first see the sequence diagram of generators and transformers that is going to help in making the equivalent circuit diagram during the faults. So for the sequence diagrams for generators, the key point is that generators only produce positive sequence voltages, therefore only the positive sequence has a voltage source. And this is the overall sequence equation for the generators. And you can may also say that during the fault, this positive sequence impedance is approximately equal to negative sequence impedances, and it is also equal to subtransient reactance of generator. This zero sequence impedance is usually substantial, very small. That's why the value represented depends on the whether generator is grounded or not. So these are the sequence diagrams for generator. First one is the positive sequence diagram for generator, and this negative sequence network in this just we are not taking the this voltage of generator, only this negative sequence impedance. And zero sequence network you can make like this. If this neutral is grounded, then you have to take 3 times of Zn. Otherwise you just take as zero sequence impedance of transmission line. So just revise all these things and we begin shortly the solving the gate problems. Now for the sequence diagrams for transformers, it is very important. I think this one is the most unusual, like things like how if this star or delta connected, how we have to consider, how we have to make the equivalent circuit diagram, equivalent sequence diagram for the transformer. So here in the transformers, these positive and negative sequence diagrams are similar that as that of transmission lines, and the zero sequence network depends upon both the how the transformer is grounded and the type of connection. That means how in the how it is connected, it is delta connected or a star connected, or in a star it is also of two types, either it is grounded or not. And if it is grounded, then is the grounding impedance present or not, that we have also we should consider. And the sequence and shunt switch connection for delta and star winding for transformers are represented like this. So this series connection is for the a star connection, and a star connection only if it is grounded, and this shunt connection is for the delta connection. So we will see examples based on that, so that it will clear to you. So here we are considering transformer where it is connected with the star grounded, like you can see here. So here we can see that in the primary it is delta connected, so we have closed the shunt switch. And in the secondary side, since this is star connection and it is also grounded, so we close the series switch. So the equivalent sequence diagram for this transformer connection can be make like this. Here I have noted down that this primary is delta connected, therefore the shunt switch of the primary side is closed and the series switch is left open. and the secondary is star grounded. Therefore, the series switch is closed and the shunt switch is left open. Now let us see the examples. They may ask about zero sequence diagram for a power system network in 1 mark question. They have asked previous, so it is important for you to just understand how we are going to make the sequence diagram. Now these are the 5 configurations for transformers. First one is delta delta. So this shunt switch will be closed and series switch is left open. And in the second configuration here is a star with grounded. So shunt switch are kept open and series is closed. And the third connection is a star with primary is a star and secondary is star grounded. So here this one is the figure. So here this shunt is also kept open and series is also kept open. There and in the secondary side series will be closed. And this delta and delta in the primary and a star with grounded in secondary. Delta in primary shunt will be closed and a star in a star with grounded condition in secondary, that means series will be closed. And delta star, last one is delta star connection. So delta is present, the shunt switch will be closed. Since it is star not grounded, so both switches are open. So what are the important point you have to keep in mind for zero sequence diagrams? For delta connection, you have to close the shunt switch, and for a star connection without grounded, you have to do nothing, and for a star connection with grounded, you have to close the series switch. Now let us see one of the examples based on that. So in the unbalanced
Sir,
fault, yes,
if star connection have grounded resistance, sir, or in reactance.
yes, it will be simple. It will Z naught plus 3 Zn.
Oh, okay, okay.
So it is not like that. It will means it is in series connection with the zero sequence impedance.
Okay, sir.
Now, so for the unbalanced fault system, uh, we are going we first we will see an example. So the first step for the analysis of unbalanced faults is to assemble the three sequence networks, and we have developed the sequence network for each single stage earlier, like for generator, for transformer, and for transmission line. And now we will develop the sequence network for this below example. So what are the things you have to consider in mind? For positive sequence network, you have to consider the voltage of generator or the voltage of motor. It is you can treat it as motor, you can also treat it as generator. And for the transformer, you see the how it is connected as star or delta. And for transmission line, whatever the impedance given, you have to take it as. For the transmission line, it is just simple. Means whatever the reactance value is given, you have to take that. Means suppose you are making the positive sequence network, then you have to consider the positive sequence reactance. And if you are making the negative sequence reactance, then you have to take the negative sequence reactance. So that's all. Now first we will solve this positive sequence network. So in the positive sequence network, we are considering the EMF for generator and for motor both, and all others, like since it is delta and a star connection. Sorry, delta star connection. So there nothing to related with uh, for positive sequence network. It comes into picture for zero sequence network. So for transformer, it is given as 0.1. So J 0.1 we have written down, and then for transmission line it is 0.105, and for this transformer it is 0.1, and for the motor this reactance is given 0.2 and this EMF is given. And for negative sequence network you have to do nothing, just remove the EMF, so that will be the equivalent negative sequence network. And for zero sequence network you have to see the star delta connection of transformer. So both side you can see that it is delta, so shunt switch will be closed, and a star side it is also grounded, so series connection will be closed. So both the generator and motor bit will be isolated in the negative sequence, in zero sequence network, and this shunt switch is closed. That's why it in this figure is made like this. Till here is any doubt? Any doubt? So if you don't have any doubt, then we can move to the first problem. So the first problem is that a generator is connected to a transformer which feeds another transformer through a short feeder. The zero sequence impedance values are expressed in per unit on a common base and are indicated in figure. The Thevenin equivalent zero sequence impedance at point B in per unit is. So this problem is asked in GATE 2002. It is of 2 marks. You also try yourself. So we have seen in detail how we are going to make the zero sequence reactance diagram. So zero sequence reactance diagram. So here first we will make the zero sequence reactance diagram for generator. So it is x naught is j 0.03, and this resistance is connected, so it is 3 times of Zn. So whatever the value, so we have to do it multiplication with 3 times, so it is come as 0.75 resistance value. Now this transformer, that is the important part for zero sequence reactance diagram. So this should be not closed series connection because it is delta connected. So you just keep it left open and connect this parallel switch, and the zero sequence reactance for transformer is J 0.1. Now secondary side it is delta connection, so it will be closed, and this will be open. Shunt connection will be open. Sorry, secondary side is a star with grounded condition, so it is series will be closed and shunt will be open. And now we have transmission line, it is J 0.05. Now it is star with grounded, so it will be closed and shunt will be open. You can make a shorter way, but for better understanding, I'm making whole figure. You can make in a half a minute also. And for transformer, it is J 0.07. Now it is grounded. So take it as 3 times of Zn. So 3 into 0.25, 0.75. And this point is B. Now they have asked about this equivalent Thevenin zero sequence impedance. So what will be the equivalent zero Thevenin impedance? Just you have to do the series connection of resistant inductance, that is 0.75 plus J of 0.1, how much, 0.22, J 0.22. So correct answer is B. So now let us come to the unsymmetrical faults. So basically in unsymmetrical faults we study three types of fault: single line to ground fault, line to line fault, and line to line ground fault. So after these faults, the system becomes unbalanced, and therefore we have to do the we have to do the symmetrical component analysis in this fault while doing the unsymmetrical fault analysis. So the unbalance the network, but only at the fault location. This causes a coupling of the sequence networks. How the sequence networks are coupled depends on the fault type. So we will derive these relations for the several common faults. With a single line ground fault, only one phase has non-zero fault current. We will assume it as a phase A. So first case is that we will consider without fault impedance. There is no impedance while fault is happening at the phase A. So what are the boundary conditions? VA is equal to 0, IV is equal to 0, and IC is equal to 0, and the fault current is IF is equal to IA. Anil, is there any doubt till here?
No, sir.
Okay. So you have to derive the what is the fault current and what is the equivalent circuit diagram for the generator during LG fault. So based on these boundary conditions, we put all these values. So we are unknown is IA, that is fault current, IV is 0, IC is 0. Basically we assume this B and C current 0, so that our calculation is easier and we can do the simplification. So that is the first thing while doing the fault analysis. Now we will use this symmetrical component equations. So symmetrical matrix where we can find IA0, IA1, IA2, IA2 within the having with the boundary conditions. So we can see that IA0, IA1, IA2 is equal to 1 by third of IA. So this is unknown is IA, other one is 0. So all sequence current equations are equal to 1 by third of IA. Therefore fault current will be 3 times of IA1, and it is 3 times of EA divided by Z0 plus Z1 plus Z2. And the sequence network equation you can make with the help of this equivalent circuit diagram. So VA0 is equal to, okay, I think the mistake in this figure. This is VA1, this is VA2, and this is VA0. So VA0 will be minus IN0 Z0, and VA1 is EA minus IA1 Z1, and VA2 minus IA2 Z2. Now with the fault impedance, let us assume this LG fault occurs on phase A with fault impedance as ZF, and here this boundary condition just at previous conditions we have VA is equal to 0. Now it becomes IA into ZF, and the other things are remain same. IV is equal to 0, IC is equal to 0, and the fault current is also same. IF is equal to IA. So in this same, if we found the symmetrical component currents, then all currents are equal, and it is one third of the phase current. So it is IA, and the fault current will be IF is equal to IA is equal to 3 IA1, and this is the this is the important equations for the LG fault. And based on this figure, you can make this equivalent. You can write the sequence network equations. Now the question comes here that why we have made this in series connections, that VA is equal to VA0 plus VA1 plus VA2. Why is not other configurations? The answer is that we have we know that this fault voltage, that is fault at this phase A is equal to IA into ZF, and if you put this in this is symmetrical balance symmetrical component equations, then VA is equal to VA0 plus VA1 plus VA2. So the only way these two constants, that is all these current equations are equal, and this VA is equal to VA0 plus VA1 plus VA2 is satisfied by this coupling the sequence network in series. Now with the sequence network in series, we can solve for the fault currents. Here we have assumed ZF is equal to 0. That is the example we have taken. So just put this expression and you will get the positive sequence current, and from there you can get the fault current. It is 3 times of positive sequence current, so we'll get minus j 5.8 ampere, minus j 5.8 per unit. So coming to the problems, so let us solve the first problems on this LG fault. So here this problem is asked in GATE 2004, and it is of 2 marks. So here a 500 MVA 50 Hz 3-phase turbo generator produces power at 22 kV. Generator is star connected and it is neutral is solidly grounded. Its sequence reactances are x1 is equal to x2 is equal to 0.15 and x0 is equal to 0.05 per unit. It is operating at rated voltage and disconnected from the rest of system, that is no load. The magnitude of the sub-transient line current for a single line to ground fault at the generator terminal per unit will be. So first make the equivalent reactance diagram for this LG fault. X1 is given as J 0.15, and X2 is given as J 0.15, X0 is given as J 0.05. So this is VA1, this is VA2, and this is VA0, and it is EA, and all the symmetrical Component currents are equal in the LG fault, in the single line to ground fault. So we know that IA1 is equal to IA2 is equal to IA0 is equal to EA divided by JX1 plus X2 plus X naught. So no neutral impedance is there. Here it is given that it is solidly grounded. That means neutral impedance is 0. So EA is 1 at the angle of 0. We assume it. So it is J 0.15 plus J 0.15. So it is 1 at the angle of 0 degree divided by J 0.35 minus J 2.857 per unit. So now it is asking about the line current for a single LG fault at the generator terminal. So the line current will be IA is equal to 3 times of IA1, 3 into, take the magnitude only, 3 into 2.857 per unit. So it is coming as 8.57 per unit. So it is approximately coming close to D option, 8.553. So it is one of the easiest problem on the LG fault, and it is of 2 marks. Now let us see the next problem, and this is common data question for 2 problems. That means it is of 4 marks, and this is asked in GATE 2005. So it contains 2 sub questions, and the first question is also of 2 marks, and the second question in this is it is also of 2 marks. So in the first question, so let us read the problem. At a 220 kV substation of a power system, it is given that the three-phase fault level of is 4000 MVA and single line to ground fault is 5000 MVA. Neglecting the resistance and the susceptance of the system, the positive sequence driving point reactance at the bus is. So you have given that two short circuit MVA capacity, that is for three-phase fault and the LG fault, means for balanced fault and for unbalanced fault also. So for here it is asking about positive sequence driving point reactance. So from the three-phase fault level, we can find the fault current. We can find the fault current. So first we are analyzing the three-phase fault, and then from that we can find the positive sequence reactance. Since three-phase fault is balanced, so is there negative sequence reactance or zero sequence reactance present in the three-phase fault? Can anyone tell
No, sir.
why this positive sequence reactance is only present in three-phase fault?
Mm, because the system is balanced and balanced is positive sequence and negative sequence will cancel out to each other and zero sequence.
Yeah, negative sequence have no meaning. That will that
Yes, sir.
that will have zero value. Three-phase fault level is, we can write root 3 times VF IF Three phase fault is 4000 MVA. 4000 to 10 to the power 6 root 3 into VF. The pre-fault line voltage is 220 kV. So 220 into 10 to the power 3 into IF. So it will give the fault current, actual fault current. So it is coming as 10.497 kilo ampere. Now this fault current is coming at 10.497 ampere, and we know that fault current is equal to like you can say phase voltage divided by x1 for three phase fault analysis. In case of three phase fault, IF is equal to VA divided by x1. So it's better to write, this is phase voltage, so it's better to write VF divided by root 3. So it will give you as 220 divided by root 3 divided by x1. Since IF is given as 10.497 kilo ampere, 10 to the power 2 3, so 220 divided by root 3, and it is also in kilovolt. So on simplification you will get x1 as 12.1 ohm. So x1 value is coming as 12.1 ohm. And the next problem, it is having the same data and it is also of 2 marks. Here they are asking about zero sequence. So we have found the positive sequence reactance. So this is not going to change for the certain power system. So x1 we have found 12.1 ohm from the three phase fault analysis. Now the second thing is given as LG fault is given as 5000 MVA, but negative sequence reactance is not given. So we can just assume it is equivalently equal to positive sequence. So we are assuming x2 is equal to x1. This type of problem I don't think if they set and means like 2024 or some upcoming GATE exam, they will definitely give the negative sequence reactance. Otherwise, nowadays a student will not going means ask for marks if something is problem is happening any problem. So at that time they have not given the negative sequence reactance, but generally we can take it as equal to positive sequence reactance. And we have to find the zero sequence reactance. For LG fault, let us first find the fault current, actual fault current, because three phase fault level is given. So three phase fault level is root 3 times of VF IF, and it is of 5000 MVA root 3 times of 220 into 10 to the power 3 into IF. So IF will be 13.12 kilo ampere. So we can find the sequence current in LG fault now. Sequence currents in LG fault. So we know that for LG fault, all sequence currents are equal. So it is IA1 is equal to IA2 equal to IA0, and it is equal to IA divided by 3. So IA is fault current. So fault current is 13.12 kilo ampere divided by 3. So it is coming as 4.37 kilo ampere. So from IA we know that IA is equal to EA divided by Z1 plus Z2 plus Z0. Better to write in X1 term. So EA divided by X1 plus X2 plus X0. And here we are taking all the actual values. So in actual values we are going to put this all actual values. So it is 4.37 into 10 to the power 3, and phase voltage is 220 divided by root 3, and x1 x2 is 2 into 12.1 plus x naught. So from here x naught will come as 4.84 ohm. So B option is correct. One thing is good in this problem is that options are have a difference, and from the means like after solving if you not get the option then it may be incorrect. So you may think that what things you have done incorrect. Like here many of you can take this as line voltage, but we have to consider this as a phase voltage because we have seen the equivalent circuit diagram, and we always consider it is occurring it is single line to ground fault also. So it is occurring in one phase. So the phase voltage is 220 divided by root 3. Now let us see the next problem. So this problem is asked in GATE 2014, and it is also of 2 marks. Fault analysis problems are very simple, and it you can easily solve just knowing all the equivalent reactance diagram during each type of fault, like LG fault, double L fault, line to line fault, or line to line ground fault. Nothing is much more complicated in the fault analysis. So here a three-phase 100 MVA 25 kV generator are solidly grounded neutral, and the positive, negative, and the zero sequence reactances of the generator are zero point 0.2 per unit, 0.2 per unit, and 0.05 per unit respectively at the machine base quantities. If a voltage single phase to ground fault occurs at the terminal of unloaded generator, the fault currents in amperes immediately after the fault is. So here this voltage single line to ground fault occurs. Voltage means this neutral impedance is 0. So we can find this first symmetrical currents, sequence currents. So sequence currents in LG fault will be IA1 is equal to IA2 is equal to IA0 equal to EA divided by Z1 plus Z2 plus Z naught. EA is 1 at the angle of 0 degree. Reactances are J0.02 plus J0.02 plus J0.05. So it will be 1 at the angle of 0 degree divided by J0.45. So this will be minus of J2.22 per unit. So fault current will be fault current is IF is equal to IA is equal to root 3 times of sequence currents, positive sequence current, 3 times of minus J2.2 per unit. So it will give you as minus J6.67 per unit. So all these values are in per unit. Now here in this problem it is asked about the fault currents in amperes. So IF actual current will be IF per unit into I base. So it will be equal to IF per unit. IA base we can write S base divided by root 3 into V base LL. So IA per unit will be 6.67. S base is 100 MVA divided by root 3 times of V base LL, that is 25 into 10 to the power 3. So it will come as 15.396 kilo ampere. But in the problem it is asked that in ampere. Then 15,396 ampere. So it is the answer 15,396 ampere. So you can see that they get examiners has asked so many problems on the fault analysis, but you have to just remember one simple expression, that is sequence currents in LG fault are same, positive, negative and zero sequence currents are same, and the fault current is 3 times of sequence current. That's it. You can easily solve the LG fault problems. Now the next problem, it is asked in GATE 2017. GATE 2017 set 1, and it is of 2 marks. So all of you try this problem. Ritesh, Anil, Koteswar. So basically I am in different country, so time is showing different here. So this the problem says that the positive, negative and zero sequence reactances of a star connected synchronous generator are 0.2 per unit, 0.2 per unit and x and 0.1 per unit respectively. So what are the things we have given? Positive sequence reactance is given as 0.2 per unit and negative sequence is also 0.2 per unit and zero sequence reactance is 0.01 per unit, 0.1 per unit. and the generator is an open circuited with terminal voltage of 1 per unit. The minimum value of the inductive reactance in per unit required to be connected between neutral and ground. You have to find the inductive reactance in per unit that is connected to neutral and ground so that fault current does not exceed 3.75 per unit if a single LG fault occurs at terminal is. So the fault current is limited up to 3.75 ampere, and we have assumed this fault is happening at phase A, so it is restricted to 3.75 per unit is given, and it is asked that what will be the inductive reactance that is connected with neutral and ground so that this fault current is limited to 3.75 per unit. So it is also a very simple problem. We know that for a LG fault, the sequence component currents are IA1, IA2, IA0 equal to EA divided by x1 plus x2 plus x naught plus 3 times of xn, and fault current is 3 times of IA1. x1 plus x2 plus x naught plus 3 times of xn. So 3.75 equal to 3 into 1 divided by x1 is 0.2 plus 0.2 plus 0.1 plus 3 xn. Xn we have to find. So it will become as 0.5 plus 3 times of xn, that is 0.3 divided by 3.75, it is 0.8. So xn will be 0.1 per unit. So the correct answer for this problem is 0.1.
Hello.
Yes.
Sir, this call will end in 15 minutes. Sir, last time is also happening this, and I join again this class, but I'm not able to join.
Yeah. So I am sending you one link. Actually,
Yes, sir.
this link you join. I will join because I am in different country. Right now I'm in Germany. So
Okay,
this
sir.
problem is happening if you outside India. So I've shared one link.
Uh,
So you can join by this link after 1 hour.
yes, sir.
Uh, sure. And just copy this link. Otherwise, because this uh, if this meeting ends
Yes,
now,
sir. If this meeting is end, then the link will automatically
yeah,
finish, sir.
just copy this link and we will join by that.
Okay, sir.
Now let us see the next problem, and kindly turn off your mic, Ankit. The next problem is that, yeah. So here again, this is problem for LG fault, and in this problem it is given that the positive, negative, and zero sequence impedances of a to 125 MVA three phase 15.5 kV a star grounded 50 Hz generator are J 0.1 per unit, J 0.05 per unit, and J 0.01 per unit respectively on the machine rating base. The machine is unloaded and working at the rated terminal voltage. If the grounding impedance of the generator is J 0.0 per unit, then the magnitude of fault current for a phase B to ground fault in is you have to give the answer in two decimal places. Okay, so what are the things just be, and this problem is asked in GATE 2018, and now they have reduced the marks and it is of 1 mark. Earlier, whatever problems they are asking on LG fault, they are of 2 marks, and in GATE 2018, they have asked it of 1 mark. So here given things are x1 is equal to j 0.1 per unit and x2 is given as 0.05 per unit, x naught is equal to 0.01 per unit on the machine rating base, and the grounding impedance generator is also given. So xn is given as 0.001 per unit. And the magnitude of fault current for a B phase to ground. So they may many students they want to confuse that it is of phase B. So we have to do analysis in phase A. So it may differ for phase B or it may not. So the answer is no. It is similar for all the phase. So whatever the LG fault is happening, then the fault current will become similar. So for LG fault, we can write the sequence component currents for LG fault. IF is equal to, here it is given as IB, so it is 3 times of E, 3 times of EMF divided by Z1, and you can write here EB, 3 times of EB divided by X1 plus X2 plus X0 plus 3XN. So 3 into 1 at the angle of 0 divided by x1 is j 0.1. So you can take j also here, 0.05 plus x naught is j 0.01, 3x, so 0.03. So it will be 3 divided by j 0.19, it is minus of j 15.789 per unit. So we have to give in answer in actual current. So IF actual will be IF per unit into I base. So IF per unit, I base is S base divided by root 3 into VLL base. Just put all these values. IF per unit is 15.789, S base is 125 MVA, root 3 times of VLL, 15.5 into 10 to the power 3. So it is coming as 73.51658. 73.51658. It is approximately, if you round up to two decimal places, it is coming as 73.52 kilo ampere. So the correct answer is 73.52. So coming to the next problem. So here the here in this problem. First, let us see when it has been asked. So it is asked in GATE 2019, one of the toughest exam, one of the easiest exam for electrical engineers. That is GATE 2019, and it is of 2 marks. So a 30 kV 50 Hz 50 MVA generator has the positive, negative, and zero sequence reactances of 0.25 per unit, 0.15 per unit, and 0.05 per unit respectively. So given values are x1 is equal to 0.25 per unit, x2 is 0.15 per unit, and x0 is 0.05 per unit. And neutral of the generator is grounded with a reactance so that the fault current for a voltage LG fault and that of a voltage three-phase fault at the generator terminal are equal. Okay, means for the LG fault and three-phase fault, this fault current is same. The value of grounding reactance should be. So what should be the grounding reactance value should keep so that the fault current for a LG fault and three-phase fault will come as equal. So for three-phase fault, this zero sequence current will not come, zero sequence reactance will not come into picture. So there is no relation. But for LG fault, it comes. So first, let us write the equation for LG fault. For LG fault, the fault current is IF is equal to 3 times of EA divided by x1 plus x2 plus x0 plus 3 times of neutral reactance. So let us take it as first expression, and for three-phase fault, fault current will be this positive sequence reactance just will present and not this negative sequence and zero sequence reactance will present. So for three-phase fault, fault current will be EA divided by x1 only, phase voltage divided by x1, and we are writing in per unit, it is another way. So this is the second equation. Now it is given that both fault currents are equal. Given that both fault currents are equal. So 3 times of EA divided by x1 plus x2 plus x0 plus 3xn divided by is equal to EA divided by x1. So EA get cancelled out. So we can write 3x1 is equal to x1 plus x2 plus x0 plus 3xn. So it is 2x1 is equal to x2 plus x0 plus 3xn. Just put all these values, you will get xn is equal to 0.1 per unit. So we have to give the answer in decimal. Now we have to find the Z base first so that we can find the actual reactance. So Z base, we all know that. Can anyone tell what is the expression of Z base? Anil?
MVA upon kV square.
No, Z base is uh,
Sir, kV base square divided by MVA.
yeah,
kV base is
yeah.
square divided by MVA.
correct. So we have found xn in per unit. So xn in ohm will be xn in per unit into kV base square divided by MVA base. So it is 0.1 into kV base is 30 square, MVA base is 50 MVA. So it will become as 1.8 ohm. So the correct answer for this problem is 1.8, and they have given the range as 1.7 to 1.9. So now the last problem we are going to see on the LG fault, and then we will start the line to line fault. So here,
Sir, sir, one
yes,
minute to go.
yeah,
This call will end in 1 minute, sir.
okay, so we join another meeting. So we are closing this meeting, and all of you join.
Sir, 1 second. Please give that link, sir.
Yes, I am closing this session. Is the screen visible? Hello, hello. Can you tell Ritesh, Anil, Koteswar? A screen is coming. Hello.
Yes, sir.
Okay, fine. So let us see this problem. It is in asked in GATE 2003. From the question, anyone can afraid like it is too long. But if you see that they are very easy problem. So GATE 2003, and it is of 2 marks. So here they have given one alternator that is connected to a three-phase transmission line, and the per unit positive sequence, negative sequence, and zero sequence of alternator they have given. Like what are the things given there? So we can write like this. They have given x1g as 0.1 per unit and x2g as 0.1 per unit and x0g as 0.1 per unit, sorry, 0.04 per unit. And for line, and the neutral alternator is connected to ground through an inductive reactor of J 0.05 per unit. So Xn, so Xn is given as J 0.05 per unit. The per unit positive negative sequence of transmission line is also given. So for transmission line we can represent as X1L 0.1 per unit, and negative is 0.1 per unit, and it is 0 sequence 0.3 per unit. All per unit values are based on the machine ratings. A solid ground fault occurs on one phase at the far end of the transmission line. The the value of alternator neutral with respect to ground during the fault is. Here they have asked about the voltage of the alternator neutral with respect to the ground. So how you can find, basically the thing is that we are one generator and this transmission line is there at the far end of the transmission line. So like fault is happening at the far end of transmission line. Here you have to find the voltage alternator neutral with respect to ground during the fault. So first we have to find the fault current, because that fault current will flow to the neutral reactance of the alternator, and that will be helps in finding the neutral voltage with respect to the ground. So let us first find this equivalent sequence impedances, equivalent sequence reactances, equivalent sequence reactances. So x1 equivalent is x1g plus x1l, so it is 0.2 per unit, and x2 equivalent is x2g plus x2l, so it is also 0.2 per unit, and x0 equivalent, so x0 sequence equivalent reactance is x0g plus xol plus 3 times of xn, so it is 0.04 plus 0.3 plus 0.15, so it is 0.49 per unit. Now we make the equivalent sequence reactance for LG fault. For LG fault, it is like this. X1 equivalent, and this is X2 equivalent. This is X0 equivalent. This is IA0 is equal to IA1 is equal to IA2, and EA is equal to 1 at the angle of 0 degree. This one is VA1, IA1, IA2, VA2. This is IA0, this is VA0. So first finding the sequence component currents. So IA1, IA2 is equal to IA0 is equal to EA divided by X1 equivalent plus X2 equivalent plus X0 equivalent. So it is 1 at the angle of 0 degree divided by J 0.2 plus 0.49. So it will become as minus of J 1.1236 per unit. So fault current is, therefore fault current is 3 times of sequence currents. So 3 IA1. So it is minus J of 3.3708 per unit. Now how we can find the voltage of neutral with respect to ground? So voltage of neutral with respect to ground. So we have that we have to find this Vn, and Vn we can write that If into Zn. So If we have found this as 3.3708 and Zn is given as 0.05. So this is coming as 0.16854 per unit, and you have to give the answer in the actual actual value. We have found this in per unit value. So the actual base value is, so Vn actual will be Vn per unit, and base value is given as 6.6. It is in line voltage, so you have to convert in phase voltage. So divide by root 3 into 10 to power 3. So it will give you as 0.16854 into 6.6 divided by root 3 into 10 to the power 3. It will give you 642.2 volt. So the correct answer is D option. Any doubt in this problem? Anil Koteswar?
Clear, sir.
Hmm? Yes?
Clear, sir. Got it, sir.
Okay, okay. Fine, then we can move to the, so this is all for LG fault. Now we are moving towards the LL faults, line to line fault. So the second most common type of fault is line to line. After the LG fault, that is the most chance of occurrence in the power system. So it occurs when two of the conductors come in contact with each other without loss of generality. We will assume phases B and C. So here we are assuming this fault is happening within the phase B and phase C. So in the previous case, just similar in this case also, we will consider first case as without fault impedance, that is ZF is equal to 0. Therefore, the boundary conditions are IA equal to 0, because this is the assumption we have taken, and IV is equal to, we have taken the assumption that no load is connected before the fault. So that's why I is equal to 0, and IV is equal to minus IC, and I 0 is equal to 0 because no grounding part is coming into this coming in this fault and LL fault, and VV is equal to VC because these two phases are in short circuit condition. Now based on the boundary conditions, we will apply the symmetrical component equation, and from there we will derive some important equations. So here we can see that we put that IA is equal to 0, IB is equal to IGT, and IC is equal to minus IB. So this IA 0 will be 0. You can see from this symmetrical component equation also, and other way, in an analytical way, you can also say that since no grounding condition is coming to this fault, so this zero sequence component of current will be 0, and positive sequence component of current will be uh, this much, and negative sequence current will be this much. So by comparing both these two equations, you can say that IA1 is equal to minus IA2. So to satisfy IA1 is equal to minus IA2, and this VA1 is equal to VA2, and how is this coming? VA1 is equal to VA2 by solving this equation. VV is equal to VC. You solve this equation, then this comes VA1 is equal to VA2. I think, yeah. So these equations, VA1 is equal to VA2 by solving VV is equal to VC. From there, you will get VA1 is equal to VA2. So the first we got from the symmetrical component equation that IA1 is equal to minus IA2. So to satisfy both these equations, we can make the equivalent circuit diagram during line to line fault. Sorry. So the positive and negative sequence networks must be connected in parallel because this VA1 is equal to VA2, and there is no zero sequence component current because there is no path to ground. So VA1 is equal to VA2, we can see here, and IA1 is equal to I2. So we will connect in this way. And now we have to find the fault current. How we are going to find this fault current? IF. And IF is just equal to IB or equal to minus IC. So how we are going to find? I will just write some of the expressions so that you can get how we are getting this. So IF is equal to IB, you can write. So IB we can write into symmetrical components. IB0 plus IB1 plus IB2. No ground is there, so it will be 0 IB0, and IB1 will be lambda square IA1. We can write like this, and IB2 will be lambda into IA2. And in the previous case, we have solved that IA1 is equal to minus IA2. So we can write lambda square minus lambda IA1. And lambda square minus lambda will be minus j root 3. So from there, you can find the fault current in line to line faults. And after making this equivalent circuit diagram during LL fault, you can write the sequence network equations just by following the KVL. So this is the most important part for any fault. You have to remember this fault current so that you can solve the problems in GATE exam. Now we
Sir,
can,
at last we have to consider that mod value, no, sir. IF
yeah,
magnitude.
yeah, mod value. This we neglect because they don't care about this reference to whatever the reference. So we neglect this minus j.
Okay, sir.
You can solve by putting this also, but at the end you have to neglect because nobody cares about this. Uh, it is as minus j or plus j or something having angle. Angle doesn't matter. Na. They are asking about the magnitude only. So with fault impedance, just as previous case, we here this VV is equal to VC plus IB plus ZF comes into picture. So in the previous case, we have assumed the fault occurs on phase B and phase C. So here we are considering this fault impedance ZF. So IA is equal to 0 because we are considering unloaded condition, and this IB is equal to minus IC, and I0 is equal to 0 since no ground is present. And they and from VV minus VC is equal to ZF IV, one can prove VA1 minus VA2 ZF IA1. So like previous case, if ZF is equal to 0, then VA1 is equal to VA2, means positive sequence voltage equal to negative sequence voltage. Now to satisfy both these equations, IA1 is equal to minus IA2 and VA1 is equal to VA2 plus ZF IA1, the equivalent circuit diagram can be drawn. And therefore this fault current you can write in this way, and you will get the fault current like this. So it is the same proof as before I did, and the sequence network equations can be written from the equivalent circuit diagram. I think this is large slide, yes. So unfortunately I would not cover all the unsymmetrical fault analysis, so I will try to cover in the next class, means I think all problems based on the fault analysis, so that you have a good confidence on the fault analysis. So any doubt or anything? I think next class will be the last class for this NPTEL GATE PMRF. That's why they are asked us to do the 2 hour session. But I think it is only 1 hour 15 or 20 minutes. Anil Koteswar it is. You just don't think too much. Whatever things you can do, what is in your hand, just do that. And all the best for means upcoming GATE exam. We have time, but just revise and solve problems. That is enough. And make short notes also. Short notes helps during last time. They will boost up your confidence at the last moment, because before GATE exam you cannot solve problems like 1 or 2 or 3 days before. Means 1 or 2 days before, just stop giving test series and anything. Just you have the short notes. 2 days before, whatever things you do, just do. But 1 or 2 days you could not give test series or solving problems. Just revise short notes and go to the GATE exam. Any doubts, any concern, just ask me. Otherwise, we will meet in the next session. And that is the means like suggestion for you all. Don't afraid that much of GATE exam. If you afraid, then you will just lose confidence and you will do nothing. Means like whatever you can do, you do. Whatever things you like, that study means I think like you could not cover whole of the syllabus, but whatever the syllabus you are able to cover, just cover that, because some of the problems are related to other subjects also. And by chance, if you if from that part from that you have not solved, not that much practice, you may solve during GATE exam. How many of are you going to give the GATE exam this year?
Yes, I am, sir.
Okay, only Koteswar. Other one? Anil,
I am
Ritesh,
also giving, sir.
Anil, Anil. I think he's not here. Okay, miss all the miss we have time. Just start preparing. We will meet in the next session. If any concern, any doubt, you can ask me.
Sir, through your mail ID, sir.
Yeah,
If you have any doubts.
yeah, you can mail me, but I will try to give the answer. But I am also right now, means I am in another country, so very difficult to manage all things. I may not give an
Okay.
answer because for the next
Could
year,
you please share your number, sir? It will be helpful.
uh, you can mail me. I will send you the number.
Okay, sir. Okay, sir. That will be fine.
Other thing, any other thing?
Sir, make which type short notes means numerical short notes or subject theoretical short notes?
Numerical you formula for everything, means like whatever the expression and formulas that are basically they are going to ask, not make too many make short notes like from the resonance condition in network theory. I saw many difficult equations are there. Just don't write those equations in your short notes, because you can derive this equation very easily 1 or 2 minutes. That will just headache your mind. So means whatever the things that is going to ask in exam, that thing you just keep in your short notes. Otherwise, if you don't know that, means like if you are not remembering that equation, then don't keep in your short notes, because at the last moment you are keep remembering that formula or expression and you will forget other things. In it's my personal suggestion. So many things are like you can self derive. So whatever the important thing, from that you can recapitulate everything, so that you keep in your short notes. And the means other things like theoretical part, many many things are there that always creates confusion or you don't understood. So that things you can keep in short notes also. Like for measurement part, you may have many theoretical things like means where you have to take the average or where you have to take the RMS value. So you have to take that note also for theoretical, but you definitely don't keep the whole definition or something like that. For measurement, you have to, I think, you have to keep some theoretical aspects also. For electrical measurement subject, you have to keep that one thing and make. I think in when I gave GATE exam at that time, I just what I did, I bought 10 rupees copy for each and every uh, subject. So I have 10 to 12 copies and I kept separate because if you mug up in one copy, one notes, then it is also difficult to revise. So I make different notes, different short notes for different subjects. In not don't in one diary or one thing. It's your wish. It's not like whatever things I am do that is the correct only. But one thing follow, we are only give suggestion. You have whatever things you think correct that you follow. Don't because this is online yugna. Online yug means like there are so many videos and suggestions you can get easily. So they may sometime divert you. Means whatever things that is going to help, follow that. Not indulge in too many online things. Because I saw many students they are following so many video lectures. So maybe at the end they got nothing because I think you should follow one video lecture, one books because you don't have that much time. After completion your bachelor, you are going for masters or PhD. At that time you think like that I will do master, I will do deep research in this thing. At that time you just go deep in that thing. But if you think that I will batch this fault, means not in my subject, if you batch fault analysis from here, there, so many videos are there. But you will, same thing you will get, more or less same thing you will get. But that will kill your time only. Okay, Ritesh, that's enough for today. You will make get.
Yes. Thank you, sir.
Okay, Ritesh, Anil, Koteswar. Bye bye. Have a nice day.